Oui, voilà.
Mais il m'a dit, en fait, moi, il m'a dit, tu sais qu'en gros, ça s'appelle bien. Moi, je me prends. Le jeu, il avait ça. Peut-être qu'il y a maintenant. Peut-être tellement sur le point.
J'attends Yaline, non, il y a Mazia.
Dès que Lenny est
Ouais.
online, tu le dis.
Ok, bah, elle vient de se connecter à l'instant.
Bonjour.
Bonjour.
Bonjour. Ok, bah, tout le monde est là.
Okay. Speak English, probably, maybe not.
I will speak in English. So,
You
yeah.
speak in English?
Yeah.
Okay, so welcome for this PhD defense. I'm from Paris-Sport, and I'm professor here at UGA, one of the at university, and I'm going to be the president of the jury of the PhD of Marco. And I will introduce the jury. First, the people who are coming from, and who are not here, in fact, because they are still in Paris. There is Eleni Diamanti. I don't know how we won't see Eleni, who is directeur de recherche at CNRS, on the bottom here. And then we have Mazia Miraimi. Yeah, he's in the middle, who is directeur de recherche at INRIA. And then we have Patrice, also from Paris, who came here and is director of the research at the CEA. We have also Maud Binet, who is an ingenious doctoress at CEA Grenoble, and I think I did not forget anyone. And of course, we have the two advisors of Marco. So Marco, you have approximately 45 minutes.
Okay.
And then there's going to be the session with no limits for the questions.
Okay, so thank you everyone for joining this presentation. So my name is Marco Febosasiani, and I will present you this PhD called the Resource Cost of Large-Scale Quantum Computing, which has been supervised by Alexia Ofev and Robert Whitney. So thank you for the member of the jury for having accepted to be part of these events. So, okay. So before talking about quantum computer, I will talk about classical computer. In classical computer, the fundamental unit of information is the bit, which is either in 0 or in 1. And with that, we can do a lot of calculation. With quantum computer, the fundamental unit of information is the qubit. So it's a state that can be at the same time in the state 0 and in the state 1, thanks to quantum superposition. And to some extent, because classical computer work with bits and not qubits, so because they work with bits and not qubits, they are limited to perform some tasks. So typically, if we want to describe state of large molecule, describing an arbitrary quantum state composed of 300 qubits, you will need more bits than the number of atoms in the universe. So classical computers are intrinsically limited to some tasks, and memory limitation is an example. A quantum computer, on the other hand, will require 300 qubits only to represent this state. So it's possible to represent it easier with a quantum computer. There are other examples which are that quantum computers, they are slow for some tasks, while we know quantum algorithms that completely outperform classical algorithm. So what does that mean? You have a problem to compute. When you increase the size of the problem, the number of operations on a classical computer will grow very fastly, while on a quantum computer, it will grow in a much slower manner. And so there are examples of such algorithm. For instance, the factoring, so breaking some code, encrypted code. On a classical computer, it will take a lot of time, while on a quantum computer, it will take few hours or even seconds. So why are we talking about quantum computer now? So it's because in the last decade, the ability to manipulate with a very high level of control quantum entities has occurred. So a few examples here. So for instance, what we call an ion trap, it's possible to isolate a unique ion in a trap and to manipulate it, and it's the building block of the ion trap quantum computer. There is also the example in which we are able to isolate single electron on a quantum dot. So we manipulate voltage, and a unique electron can be isolated. And with that, we can build a spin qubit-based quantum computer. And there are the superconducting qubits, which are central in this PhD. Here it's a bit more abstract, but basically the voltage and current are behaving in a quantum manner. And with that, we can make qubits. So superconducting qubits, for instance, they are a million times less noisy than 20 years ago, so a million times of better quality. And because of that, it allowed to create the first quantum computers. So we have examples, but typically there are two issues which are somewhat related, as we will see in the next slide. The first one is that they only have a few qubits, typically less than 100. So because of that, we cannot run large calculations. And the other issue is that the qubits are very noisy. We have typically 1 error in every 1,000 operations, and it's way too much if we want to implement large-scale algorithms. So this is why they're having an idea that emerged, which is quantum error correction, which is to say, we don't need necessarily to always improve the quality of the qubit. What we can do is software strategies that will allow us to improve on an effective manner the quality of the qubit by detecting and correcting errors. So to explain quantum error correction, actually, we can do an analogy with classical error correction. So I will call a logical bit the information I want to protect, to transmit. And this logical bit, I can encode it in one physical bit, like what is here, or in a given number of physical bits. So if I encode a logical bit with one physical bit, and a sender sends me an information, and I'm here, let's say I receive the bit 1. On a conceptual level, I cannot know if the sender wanted to send me 0, and an error occurred during the transmission, and then I received 1. Or if he wanted to send me 1, no error occurred, and I received 1. So yeah, it's a conceptual problem. I cannot be able to know that. So this is why a strategy is to instead to encode my logical information with multiple physical components. And for instance, I can ask to encode a logical bit with 3 physical bits. And then let's say I receive 0, 1, 0. I will say, okay, it's likely that the middle bit flipped, had an error, and actually he wanted to transmit me 0, 0, 0. So that's an example when we encode a logical information with multiple physical bits, we are able to resist against error. So that's the same idea with quantum error correction. I will explain a bit more, but basically here we are able to resist against 1 error, but not 2 errors. Because what could have also occurred is actually he sent me 1, 1, 1, and the 2 bits at the edge flipped. So this protocol is better than not protecting because I'm able to resist against 1 error, but I'm not able to resist against 2 errors. So in quantum error correction, that's overall the same principle, except that now we are facing laws of quantum physics. So typically, measuring can destroy the data. So if we want to detect if an error occurred, and if by measuring we destroy what we are supposed to protect, it's useless. The other issue we have is the no cloning theorem. So we cannot copy quantum information. So because of that, strategy occurred and show that it's still, despite those issues, it is still possible to do error correction. So here, that's the simplest example of error correcting code we could consider. We will protect a logical qubit with 3 physical qubits. Basically, how it works is that, so I assume I have only bit flip noise. So the only thing that can happen is that one qubit here can change its value. So what this state can be written in mathematically in a Hilbert space of dimension 8, and we have different parts. We have a part of the space where all the 3 qubits have the same value. Here we have a space in which the first qubit is different from the 2 other, and that's the same idea for all. So when we have no error, the qubit lives in the code space, everything is fine. What an error, so a qubit that flip will do is that it will lead us the information from that space and we will go into another space. So for instance, here the first qubit flipped. And now what we do is that we detect, so those spaces mathematically they are orthogonal, so we can do a measurement that will tell us in which part of the space we are. So for instance, here we will detect the first qubit is different from the 2 other, so the first qubit flips. And with that, I'm able to correct and to put back the qubits in the code space. But the thing is that what is important with this thing is that this measurement is not will never destroy the data that is encoded, because knowing the parity, if you want, the fact that one qubit is different from the other, will never tell you any information about the coefficient A and B. So it is a measurement that allows you to see an error occurred, but that does not destroy the data that was encoded. And here we can have an issue. If 2 qubit flips, we will have the same issue that in classical error correction. Well, here we will, for instance, have the 2 last qubit that flip, and we will wrongly believe that's the first one, and we'll do a wrong correction. So it's like in the classical regime. So in this work, we consider STIN code. So it's a code that is able to protect you against an arbitrary single qubit error. So here I show how to correct bit flip with the 3 qubit code, but it's not enough. We have more error. Mathematically, if we can correct what is called phase flip and bit flip, we are able to resist against an arbitrary single qubit error. So we need a better code. STIN code is an example of that. It's able to correct against an arbitrary single qubit error. And for this, it needs more physical qubit than 3, 7 physical qubits to protect a logical qubit. So actually, there are many other qubits you need around. I will go back after at it. So this is error correction. Now there is, if we want to build a quantum computer, that's not enough. We need another concept, which is fault tolerance. Why? So basically, error correction, to detect and correct error, it's a process that can be that can introduce noise during your calculation. And here I assume that the detection and correction were completely perfect, but they will not. The other thing we would like to have is to have a scheme, let's say a cooking recipe that tell me, okay, I have a code, it's able to correct against 1 error, but what if I have 2, 3, 4, n error? So fault tolerance also give you a cooking recipe to tell you, use that code in such manner. And by doing some recursive construction, you are able to resist against an arbitrary number of errors. So in this work, we consider the concatenated fault tolerant construction. That's one specific choice. The reason is that it allowed us to do analytic calculations, which were a requirement for what we wanted to do. We wanted to be sure to have, because I actually wanted to be sure at the end we'll do energetic estimation of quantum computing. And for that, we wanted to be sure to not lack any data when we do our estimations. So how the concatenated construction works? So here you have 7 physical qubits, and we use Code, it can create a logical qubit, which is better protected against errors. So technically speaking, actually, that's not the qubit that are bad or good. That's the operation we apply on them. So here we have physical gates applied on the qubit. Here are logical gates applied on the qubit. What we want, so if the error correction is implemented in a fault-tolerant manner, the first requirement is that the probability of error of the gate applied on this logical qubit is lower than the probability of error of the gates applied on the physical qubits. So let's say that we have this. So here we did a better qubit. Okay. So the principle of concatenation is to say, okay, you regroup 7 qubits to create a better one. So why not using again those 7 better qubits to create an even better one? So that's the principle of concatenation. That's recursive replacement that allow you to create better and better and better qubits. And if we want to be more quantitative, this is the formula we have when we do error correction with concatenated codes. So here, eta is the probability of error of a physical gate. So if we don't do error correction, the probability that it fails is eta. K is the level of concatenation, the number of such replacement we do. So here, 0 replacement, we have physical qubit and physical gate. First replacement, second replacement, etc. And the threshold is a constant given by the code. So we realize that if eta divided by the threshold is lower than 1, so if eta is lower than the threshold, then by increasing the value of this k here, I can make this go to 0 and make my probability of error of my logical gate go to 0. So I can reduce as much as I want the probability of error of my logical gate if I have enough concatenation, which means if I have enough physical qubits at this position. So what does the threshold mean? So it actually takes into account that quantum error correction is a noisy process. It requires additional elements which bring in noise. So basically, if the physical error is lower than the threshold, the noise you bring is low. So quantum error correction really improves the situation. But if the physical error is higher than the threshold, the noise you bring is too high. So when you will do error correction, actually, it cannot compete with the fact that you have more physical components. They all add noise, and it loses in the competition. So it's actually a competition phenomenon that is occurring. Okay, so now I will go in the result of that PhD. So I will only talk about how to scale up quantum computer with limited resources. And I will not talk about other work that we did that are more related to fundamental quantum physics. So I will talk about 2 work, but mainly about the second one, the energetic cost of large-scale quantum computing. So first, limitation in quantum computing from resource constraints. Okay, so basically, that's we have a probability of error for a logical gate, that is this one. What we will assume in this work is that the physical error grows when the size of the computer grows. So what it means is that, why are we considering that? So imagine that you have a quantum computer, you have a unique qubit inside your quantum computer. You do a gate, it has a good fidelity, let's say, so that's a good gate. Now, when you will have a quantum computer composed of millions of qubits, you will have parasitic interactions between, so possibly parasitic interaction. So it's more complicated to make a good gate when you have a unique qubit than when you have millions of qubits because of those parasitic interactions. And typically, you can expect that the physical error grows the bigger your computer gets. And the way to encode it here is to say that eta, the physical error, is growing with the level of concatenation, which means that it grows with the computer size. So that's what we consider here. So let's talk about the standard fault tolerance first. So in the standard fault tolerance, so here you have the number of concatenation you do. Here you have the probability of error of the logical gate. So when you don't do concatenation, a logical gate is a physical gate. It's not protected. So if you are higher than the threshold, when you do concatenation, the physical error grows. You should not do error correction in this regime. Quantum error correction loses in the competition. if the error is below the threshold, when you do error correction, you can reduce the noise because of the formula I showed before, and you can put it arbitrarily close to 0. So that's the standard theory. When we do this replacement now, the physical error grows with the size of the computer. So first, if the physical error was higher than the threshold, okay, you will be in the same regime. It's not, you should not do error correction. But what is more interesting is this region. In this region, the physical error is below the threshold. Maybe initially it's good to do error correction, but as this physical error grows, at some point it will get higher than the threshold, and then necessarily at the end, all those curves end up growing. So a first conclusion is that what you can expect with a noise that grows with the size of the computer is that the quantum computer is limited in accuracy. That's one conclusion. So here I will directly talk about a specific study we did in that will help me to introduce the next one. So I choose to talk about this. So the connection with limited resource. So imagine that you have a physical error that depends on a resource, such that the more the resource you have, the better your gate are. So the better the fidelity are. It means that the physical error will decrease. So the more of this resource you have, this will decrease. If you assume the total amount of resource to be fixed, it will lead to a scale-dependent noise. So a noise that grows with the size of the computer. So why is that? So let's look again at the principle of concatenation. Before I presented with how the qubits are replaced. Now it's with the gates for the example I'm doing here. But that's exactly the same principle. You have one gate when you don't do error correction. You do a first level of concatenation. This gate is being replaced by a given number of D gate. When you do a second level of concatenation, each of those gates here is replaced by exactly this scheme here. And then you will have this square gate here. So then, in terms of resource, each physical component, here it receives the total amount of resource you had initially, R. Here it receives R divided by D, the resource is being shared, and here R divided by D squared. So then, when you do this, you naturally have a noise that grows with the size of the computer because you have fewer and fewer resources for your physical gate, so your physical error grows with the size of the computer, and it gives you a law that is like this. So limited resource is connected to the fact you have a scale-dependent noise. And actually, so I will not say it's always the case, but it's likely to be the case in many scenarios if you have a scale-dependent noise. For instance, if we think about crosstalk again, the resource you can think about is the volume. If you have an infinite volume, the qubit can be put as far as you want, and then you will not have the scale-dependent noise. So, a first introduction about how the accuracy of the calculation depends on the energy you inject in that. So, very simple example, we take superconducting qubits, we will manipulate them to perform gate operation. So how do we do this? Usually, we send a light pulse, so photons, there are photons here. They will interact with your qubit, and with that, you will do a gate, a Rabi oscillation. So you will do a single qubit gate. The longer you take to do your gate, the noisier it will be because you have spontaneous emission. So per unit time, well, you induce noise, and then your qubit may lose their property. So we assume that all the qubits follow this model, that's a toy model, to understand the connection. So the faster the gate is, the less noisy it is, because the less spontaneous emission we'll have. The more photon we have in the pulse, the faster the gate will be. So then, if we assume the total number of photons to be fixed for the logical gate, each physical gate receives this number of photons, so it depends on K, and it gives you a scale-dependent noise. The noise grows with the size of the computer. So what does that mean quantitatively? So here, in the x-axis, there's the number of photons we have to do the logical gate. In the y-axis, there's the probability of error of the logical gate. So what we have, here we have dotted line, light dotted line here, and here as well. So when you don't do error correction, you follow that line that is here. And basically, you see that the more photon you inject, the lowest the probability of error on the logical gate is expected because the physical error is decreasing. Here we have the same for k equal to 1, and here the same for k equal to 2. Now we see that we have this black solid line. So this black solid line is the lowest envelope, if you want, of all the dotted lines here. So it represents the maximum accuracy, which means the minimum value of that quantity as a function of the number of photons I inject. So what is happening on that point? So basically, right before that point, I could do 0 error level of concatenation or 1 level of concatenation. If I do one level of concatenation, I will do more error correction, but I will share more my photons, so my physical error will grow. So there is a competition. Should I do error correction here or not? And you realize that that's at this moment that you should start to do error correction, not before. And when you will do this, so then the slope follow now the k equal to 1 curve, the first level of concatenation. And then you continue and you have the same behavior here. So basically, that's a competition, also another competition phenomenon that occurs between should I share my resource or not? And you realize that at this point, it's the moment it's worth to do error correction. So from this graph, we see a first connection with energetic estimation. Let's say I have a given number of photons that I can inject for my logical gate. I deduce the maximum accuracy my gate can get to. But what is more interesting is the other direction. Let's say I want to reach that accuracy. I can deduce the number of photons I need for my gate. And you deduce as well the optimal level of concatenation. So you have access to some optimization if you want to have the number of physical qubits. So this is a simple example in which we see this. We could apply it to other resources, but that's the first intuition about the connection. So in this work, I did not talk about other things we looked at, but basically when you have a scale-dependent noise, there are things that are interesting, such that, for instance, as the noise grows with the size of the computer, what can happen is that the condition on the threshold to have error correction useful at all can be much more demanding. It depends on how fast the noise grows, but you can have much more dangerous, in a way, condition on the threshold. So now I will go to the second part to do a quantitative estimation of the resource cost of quantum computing. So in this work, I will not say that's the goal of this work, but that's one interesting outcome, which will be that we will design a complete model of fault-tolerant quantum computer, so which will contain practical aspects such as cryogenics, signal generation, also fault tolerance and error correction, aspect of algorithmic, and the physics of the qubits. And we will optimize this full architecture in order to minimize the power consumption of the computer in a way that is somehow related to what we just talked about. So the question we ask, the way we phrase the problem, is we say, what is the minimum resource I must spend in order to be sure that my algorithm succeeds with a high enough rate? So what this sentence means is basically, what is the minimum resource I must spend in order to be sure that my computer does what it's supposed to do, which is give me a trustable answer. This is just what that means. But then you realize that's a problem of minimization under constraints, because the resource depends on a set of parameters that are not obvious to fix, and the success as well. So one simple example is what we did previously. There were only one parameter, the number of physical qubits per logical qubit. The more you do error correction, the more you can reduce, for instance, the more you can increase your success. But it has also a consequence on the energy you must inject, because you have more elements, so you need to provide more energy to all your elements. So what we will do here is to extend this and to show that actually we can include as many things we would like and have a full design of the quantum computer. So the goal of this is to develop a universal and multidisciplinary vision to estimate the resource of quantum computing. How does that work? So here, all what is in the circle are all the elements you have in your quantum computer. So you have quantum error correction, the algorithm, that aspect of engineering, cryogenics, the physics of the qubits. On one hand, you want a good accuracy for your algorithm. On the other one, you don't want to spend a lot. So we will see, I will show example, that the algorithm accuracy, possibly in a very indirect manner, is actually related to all that. The resource consumption as well. It's related to the algorithm that is running. Some algorithm will require more or less energy than other. Well, we will see examples. What we will do, so this is the main message of the work. Then we will apply it to examples, but that's the important thing. The minimization of the constraint will impose relationship between all those things, and we will be able to optimize at the same time aspect of quantum error correction, cryogenics, engineering, algorithmic, from the minimization of the constraint. Basically, if we change one thing here, it will impact the optimum of all the other. So this is very different from optimizing a lot. There are things that you cannot understand if you don't have all those connections. We optimize the complete thing together. So let's apply that to a complete example. So here, we're asking to find the minimum power consumption of a superconducting qubit quantum computer. So in superconducting qubits, the main source of power consumption is to remove heat at low temperatures. So to give an example, to remove 1 watt of heat at 10 millikelvin, which is the typical temperature of superconducting qubits, you need 30 kilowatt of electricity. It's very costly to remove heat. So why do we take Carnot efficiency? For 2 reasons. First, it's a good figure of merit. That's an easy number that everyone can understand. The other reason is that actually for large-scale cryogenics, they can be close to Carnot efficiency. The cryogenic of the CERN is 30% of Carnot, and it evacuates large amount of heat at 4 Kelvin. So let's take an example of how the algorithm accuracy is related to all this. Okay, so first, I would say the standard vision. The algorithm accuracy is related to the algorithm and the quantum error correction. Usually, you can define the probability of success of your algorithm by saying it's 1 minus the probability that it fails. And the probability that it fails is the probability that 1 logical gate failed in the calculation. So it is typically proportional to the number of logical gates times the probability of error of a failure of a logical gate, which is related to quantum error correction. So usually, the physical error is seen as a constant. So we have this law, and that's the fidelity of the best gate you have. So in this work, we see it as a variable, and it depends on some parameter, the temperature of the qubits, for instance. And with that, we'll be able to relate to the rest. So that's a simple example in which we can see it. So let's say you have qubits at temperature T3, low temperature. So you want to drive them, you inject photons. Those photons are, so you inject photons, so you have your signal, but around you have thermal noise. If you imagine that the signal are generated at the qubit temperature, your qubit will only be sensitive to the temperature of the cold part here. So you will only have this. So that's the number of photon of the noise. So that's not the photon we would like. That's really the noise here. So we'll have only a part in which the noise, there is only the temperature of the qubits. Now, if we generate signals at this temperature, we will also have a contribution of the noise coming from that. And that's why experimentalists typically put attenuator here. So basically, if I don't attenuate, my qubits will be sensitive to the temperature at which signal is generated, because if there is a lot of noise here, it will affect a lot of the qubits. By putting attenuator, I'm isolating from that noise, but then the signal here is being dissipated into heat. And there is here we also see a balance, a competition. We would like to attenuate a lot to minimize the noise, but if we attenuate a lot, we increase the power consumption. So that's contradictory behavior, and there are a lot of such things in a quantum computer. So here in the end, the physical error probability is related to the temperature of the qubits, the temperature at which signals are generated, and the level of attenuation we use. And basically, we see that the algorithm accuracy is related, for instance, for aspect of engineering, at which temperature should I generate my signal. Of course, aspect of cryogenic from those temperature, but also on the qubit physics, because the exact law, the physical that relates you, the physical error to those parameters, depends on how your qubits are realized experimentally. So we did this connection here. So now we will do the connection with the resource. How the power depends on all that. So here we build a model of for the quantum computer that we try to make as realistic as we could. So inside there are aspects of signal generation, heat conduction, so really practical cost. And we can establish the expression of the power as a function of those parameters that we want to optimize, which are the temperature of the qubits, the temperature at which signals are generated, the level of attenuation we put on the line, and the number of physical qubits per logical qubit. That's the one we will optimize. When you do this calculation, you realize you have 2 contributions in your power. One contribution called the static consumption. It's proportional to the number of physical qubits you have in the computer. So it means that whatever your algorithm is doing, you will have this power consumption, proportional to the number of physical qubits. There is a dynamic consumption. It depends on what exactly your algorithm is doing. It's related to the number of gates that are actually active on the quantum core. So there are 2 parts. And finding those 2 things, so the message here is that, so we'll do estimation, but it's important to not only reason on the number of physical qubits. You can have different order of magnitude between those quantities in general. Then, so that's an important part of the work, doing the complete analysis of error correction and the concatenated construction. The goal was to estimate after K level of concatenation how much physical qubit, physical gate acting in parallel we have in the quantum computer for a given algorithm. So here that's 1 physical qubit on which we do 1 gate, a second gate, a third gate. When you do error correction, the first level of concatenation, actually this gate is being replaced by all that. So each line that you see here is a logical qubit. So you have the logical data qubit, that's the one that really participates in the algorithm. but around you have ancilla qubits, which are here to detect error and tell you which correction to apply. And that's a very important part in terms of numbers that completely dominate the number of qubits you will have. So it's important to estimate all that. And that's the first level of protection, but if you want to concatenate further, each gate that you see here will be again replaced by that. And so the number of physical components really grows fastly with the level of protection. There is one important thing to consider. With this circuit, you can only do what are called Clifford operations in your quantum algorithm. So that's an example of Clifford operation. Any operation here or a product of gates in this set are called Clifford. The operation, you cannot do universal quantum computing with that. You need an extra gate, a non-Clifford one. One example is the T gate. And it has to be implemented with a different scheme than this one. It's a different recipe to do that gate. And so in the result I will show, we will approximate all the algorithms, assuming they can only done with Clifford gate. But we started to estimate the cost in resources of those gates. So it's not in the thesis, this. And we don't believe actually there will be more costly than this one if we do some mutualization of the resource. So I will talk a bit about this after. Okay, so we did an analytic estimation of that. And we can estimate, so it's approximately equal, it's not an equality. The number of physical qubits as a function of the number of logical qubits and the number of level of concatenation, and the number of gates acting in parallel as a function of the level of concatenation, and the number of logical gates acting in parallel in the algorithm. So in practice, those two things can be different, can differ by order of magnitude. So it depends, of course, on the number of on the logical qubit level. If your algorithm has a QL that is approximately equal to the number of logical gates, but also it also depends on the level of concatenation. So here we finished that. We included the quantum error correction part. So now we express everything as a function of what is happening on the logical level, the algorithm you really want to implement in the lab. And we model the rest with I did not detail, but we modeled the rest. The accuracy was always also related with all those things. That's what we discussed before. And now we impose the minimization of the constraint, which will constrain all the architecture and will allow us to find the optimal set of parameters to minimize the consumption. So now we'll show results. So again, what matters is more the general concept than the result that I show here, because they are dependent on the specific architecture and one could imagine changing the code, what could imagine not reasoning with superconducting qubits. But it's interesting to have quantitative results. So in what follow, basically, I will represent the power consumption as a function of the number of time steps you have in the algorithm, which is called the depth, usually, and the number of logical qubits participating in the algorithm. So I assume the algorithm is square shape like that. In terms of characteristics, so I won't enter all the details, but we took state of the art or close to state of the art. Of course, there are assumptions behind because we don't have we took simplifying assumption to model the qubits. But the parameter we injected, for instance, for the superconducting qubit, we assume it's 1 millisecond in terms of lifetime, which is a little bit better than the Transman today. Today it's hundreds of microseconds, but it's not very far from that. And typical value for the heat dissipated by all the components. So that's the power consumption as a function of the number of qubits, logical qubits, and the number of logical time steps in the algorithm. So as a function really of the algorithm you want to implement. Error correction is behind. So we reason in order of magnitude. So that's not the, so yeah, that's really, that's an order of magnitude estimation. So we see one first thing, when we go on the upper right part of the graph, the bigger the algorithm is, we have strong transition and it costs much more power here than here. So this is because when I increase the size of my algorithm, I have to do more and more error correction because my algorithm is longer. So my probability of error of my gates must go down to have a good accuracy. Then within each zone, the color varies as well. So for a fixed level of concatenation, the color varies. I will comment that after. So one thing that we see is that for 4 levels of concatenation, there is a lot of power. So actually all that region here, it's more than a nuclear reactor. Here we have 1 gigawatt of power consumption, and here we have more. There is a more reasonable region here and below, of course, but here it's between 1 megawatt and 1 gigawatt. So 1 megawatt is typically a high-speed train, and 1 gigawatt is a nuclear reactor. So this is a more reasonable region in terms of power consumption. So very important to understand what is happening during the optimization, because we optimize something, so there is things behind the scene. Here, that's the temperature of the qubit as a function of the number of logical qubits and the number of time steps you have in your algorithm. Here, you see on that point, the temperature of the qubit is 200 millikelvin. Here, it's 6 millikelvin. So what is happening is that basically, let's start here. The algorithm gets longer and longer and longer. So my optimization tells me, okay, you should reduce the temperature of the qubit to meet the accuracy you're supposed to find. So the temperature of the qubit is being reduced until it reaches 6 millikelvin. And here, if you want to run a larger algorithm, you have no choice. You are forced to do more error correction. And then you increase the level of concatenation. And now, because you do more error correction, the script tells you, okay, there is no need to maintain the qubit at 6 millikelvin. If you want to minimize the power consumption, here you have to increase the temperature of the qubits. So this is what is happening here. So what is very important to understand is that this is a complete multidisciplinary effect that you cannot understand reasoning in an isolated manner. Because it's at the intersection of course, the noise model of the qubits, the explanation for this variation, for instance, why we don't have the qubit, I don't know, at 10 Kelvin, is because the noise model of the qubit tells us that the noise is way too high. So behind that variation, there is the noise model of the qubit. There is the way we implement the algorithm. What I mean by that is we see that when the algorithm gets longer and longer, the qubit temperature is being reduced. It's related to the quantum error correction because it defines the two edges that are here. With another error correcting code, we could expect transition at other regions, at other points. And it's related to the engineering design because why do I want to keep the temperature the highest? Why here it's 200 millikelvin, for instance, is because I want to minimize the bill. And this comes from the fact that we reason with kernel efficiency, that we have a given model for the computer. So this is really related to the engineering design. So here, that's that's an example in which we see that in a way, all the aspects inside the quantum computer play a significant role in the optimization. And to the effect, of course, there will be quantitatively, they could be very different from another code, but we expect this kind of behavior to occur for other codes. Now, quantitatively, that's an analysis to do. So now I take specific example of algorithm that we can implement. Okay, so first typical value of power consumption. So 1 kilowatt is 1 heater. It's a typical thing you can have at home. And 10 megawatt, it's typically a classical supercomputer. So here, for instance, that the Shor algorithm applied to what is called elliptic curve cryptography to break a code that is encoded not with RSA code, but with another encryption code. Here you will spend 1 gigawatt during 10 seconds with this architecture, which is a lot, 1 gigawatt. It's a nuclear reactor, but it's only spent during 1 hour, during 10 seconds, which in terms of energy, it is 10 megawatt during 1 hour, which is a classical supercomputer running for 1 hour. So that's one thing I would like to say. The power might be high on those graphs, but if you reason in terms of energy, actually it's necessarily that high. Also, all the algorithms I represent here, you could not run them on a classical computer. It will be here. It's outside of what classical computer could have. Here, another example. So there is a Hubbard model, which is a model widely used in condensed matter. We would like to characterize the property of the ground state. So that's an algorithm that prepares the ground state of the Hubbard model. Here it will cost you 1 megawatt during 100 milliseconds, which in terms of energy, it's basically boiling water here. So again, that's a lot of power, but used for a short amount of time. So it's not necessarily energy costly. Okay. So now another thing that can be interesting is that actually it's not like an algorithm. You can only implement it like this way. You have algorithm in which you can implement of a different manner. So there is, for instance, a trade-off between the number of qubits and the size of the algorithm. You can play on one aspect or the other. And what this graph can tell you is where it's the more energy efficient or power efficient to implement your algorithm. You draw a line or the different points corresponding to all the way you can implement your algorithm, and you find where it's the most power efficient to implement it. So that's another application of that graph. One last thing about the optimization. Basically, so For another set of parameters, so I change a bit the parameter, but still staying in some regime that could be reasonable in terms of architecture. So that's a large algorithm. Let's say the power consumption, the optimal temperature at which you generate the signal. So really engineering world, this thing, as a function of the lifetime of the qubit. So this is really coming from the quantum physics world. We see that the optimal temperature at which we generate signal depends on the lifetime of the qubit, which I think is not obvious because that's two very different things. But because of this constraint, they are related in an indirect manner. So an important question is how much power can we save? So I cannot give a unique number. It really depends on the point you look at. It's also very architecture dependent. If I change a bit the performance, for instance, of the qubits or the electronic, the value can change a lot. In our plot, we found sometimes you don't gain much compared to a typical scenario. Sometimes you can get, you can reduce the bill by 100. And in regime of high consumption, I'm not talking about if it consumes 1 or 10 megawatts, it's 100 less than if you did not optimize, for instance. Okay, so now a bit about the work in progress. So that thing that we are checking about the T-gate. So as I said, we did not take into account the energetic cost of the T-gate in what I presented. So the T-gates, they are more costly to do because they have to be implemented with a different scheme. Here's one example of how we can implement them. So it's based on gate teleportation. So basically, you have to prepare an ancilla state. So that's one way to do it in a specific state here. And then you have to do this circle. So what is in the green box, it's easy to do because they are Clifford operations. So we already have estimation for that. What is complicated to do is to prepare this state. It can fail frequently. And because of that, you might need a lot of ancilla to prepare to do those gates. So that's first estimation that we believe that actually, so if we add a single T-gate, it will need, for instance, a lot of ancilla. So I don't know, 10 ancilla, because 9 of them will be used if the first one is rejected. And as it's frequent, it can be rejected a lot of time. But you will never have a unique T-gate in your algorithm. Actually, in parallel, you will expect to have a given number of T-gates. And then you ask yourself, what is the probability that all those T-gates reject their ancilla all at the same time? So taking this into consideration, we believe that if you take a common reservoir for your ancilla, you can reduce a lot the bill of preparing those states. Oh, okay, that's what I say for that. So in conclusion, so in this work, we proposed a universal in the sense that we can apply to many different architecture, a multidisciplinary approach to minimize the resource you spend to build quantum computer. We applied it to a specific architecture, but we tried to make it realistic in order to access concrete value about the energetic cost. And some general message. So the first one is that it's important to start thinking about power consumption because the bill can be high. So that's an important requirement to look at. But there are a lot of optimization that are possible to do. We presented some of them here, but for instance, if we change the quantum error correction code, the result could be drastically different. And we could imagine, for instance, surface code or CAD qubits to reduce the number of physical qubits or logical qubits, but that's an analysis to do it in a quantitative manner. But also, even in this case, I think that at some point you will necessarily face that issue of power consumption because there are many algorithms that are very demanding in terms for quantum chemistry to simulate some chemical process. And in the end, at some point, you will necessarily reach the point where you will need to optimize the thing because if it allows you to reduce the bill by a significant factor, it means it's much more scalable. Okay, so, and one last thing. So here, it can be costly in terms of power, but we saw that in terms of energy, it's not necessarily the case. So that's something I think that is important to keep in mind. There are different technological improvements possible. So just a few. So making electronics work at low temperature to generate the signal is something that can be useful. And also something else is that having an ability to disable or enable the electronics when you use or don't use it, because the number of gate acting can be very different from the number of physical qubits, and it can lead you to save, to possibly save large amount of power. And then some further possible studies. So here we took superconducting qubits. There is a natural question of which kind of quantum computer will be the most energy efficient. So it will be interesting. It gives a good basis to do a kind of benchmark in some way. a question that I find interesting is other resource than energetics to optimize. So that's not the only reason that's not the only resource that can be interesting, but I will give a specific example, which is actually we can in some way mix different resources to optimize. So what I mean is that what matters is that we minimize the cost function, actually, not necessarily a resource. And you could imagine, for instance, you don't want, I don't know, your computer to be bigger than the stadium or something like this. So what you can say is that you have the expression of the power and you have the term that diverges when you violate a condition that you don't want in your design. And in this way, you can see if the design is possible or not, actually. And to find the minimum power to reach this design, because maybe that this term that diverge will tell you, okay, you can do this, but the effect on power consumption is that you will spend 100 times more than if you did not impose that condition. So that can be something can be interesting. And one thing that I find interesting also is to compare, so to take a regime in which quantum computer and classical computer both can run algorithm, but to find if for a task they can both solve, quantum computer can be more energy efficient, because maybe it will take, maybe it's doable on a classical computer, but the quantum computer will spend 1,000 less energy to do it. So not only looking for the computational advantage, but also the advantage in terms of energy. And finally, so thank you for all the people that participated in this project. So in the red box here, that's all the people involved in the work I just presented. All the members of the group as well. And all those persons here that were not directly involved, but I could exchange with them for some technical details, and that really helped to build a model that we try to make realistic. Let's see. So thank you.
So we move to give the room or no? Now it's going to be the session for the question. So as you want, just take 2 minutes. Then you can make as much time as you want during 2 minutes. Okay, so now we're going to start with the questions, and I'm going to ask the first referee, who is here, Patrice Berthet, to start with the session of questions, and then it's going to be the turn of Nadia.
So thank you for your presentation, which was very clear, and also I would like to congratulate you because it's an interesting work about that is dealing about the very timely question, which is really the practical questions that are raised by the construction, the actual construction of a quantum machine, and as you were shown, it's a new angle of reflection that to describe it in terms of resource cost and in particular energetics, and I think indeed this work is very convincing that this is a question that needs to be addressed and that is interesting to address. So that was that's a very strong point of this work, and for that you develop a pioneering multidisciplinary approach, and so this is very interesting. So I have a few questions, and so maybe so yes, one question that I had was I think if I'm not mistaken, so I'm an experimentalist, so forgive me sometimes maybe I'm asking not very relevant questions. So is it true that in your estimate you don't take into account the energetic cost of the processing of the quantum error correction? And is it something that you have thought about? And wouldn't it need to be included in such a model?
Yeah. So thank you for the comments. And yeah, it's indeed an important question. How much classical power we need to compute the syndrome? Actually, with the STEAM code, so with the concatenated code, it's not very costly. So I can explain why. And I can do some kind of back-end development just to have a rough idea. So here, when you extract the syndrome, what you have to do? So you have here, you detect basically the Z error, so the phase flip with this qubit and the bit flip with this one. In practice, what you have to do is here you would have 7 measurements for the Z measurement and 7 for the here as well. Basically, you have 6 what is called stabilizer to measure, which means 6 different measurements to do to detect if an error occurs. And in practice, it means that you will have to compute basically on this qubit here, 3 dot products of 7-bit length, and here 3 dot product of 7-bit length. So if we do let's say a very rough estimation, let's say that each physical qubit every 100 nanoseconds, which is the clock speed, we need to compute about 1 dot product of 7 bits. So then the question is, in terms of classical computing power, when will it start to be a problem? So then what you can say is, okay, I have n physical qubit in my quantum computer. I have to compute this fundamental operation every 100 nanoseconds. And if you can write, so maybe or I can do the thing, but if you have basically this, so you have the number of physical qubits times this fundamental operation, so every 100 nanoseconds. And you realize that, for instance, for n that is equal to 10 billion here, assuming that this operation is as costly as a floating point, you end up with like something that is 10 to the 18 flops, which is a big number. But I think, so it's typical for the next generation of classical computer. I think it's 10 to the 18 flops. And here it gives you a rough estimation in the sense that, so I simplified a bit the discussion, but my point is just to say that here you don't have a lot of operation doing this kind of back-end development because it's not floating point operation, it's bitwise operation. So it's much more, it can be much less costly. So I don't think it will be costly in terms of, so I don't know if it's.
Okay, yeah, absolutely. And is it something that would be also true with other codes?
No, I don't think. So I don't know very well surface code, but from what I've heard in surface code, it's much more costly to compute the syndrome.
Yes, this is also what I.
Yeah, yeah.
So in the end, this energetics approach is also interesting.
Yes.
Also to.
Yes.
From this point of view. And what about surface code? So because this is indeed the most common say architecture that is considered nowadays, and so I understand that you need. I mean, for this, it's very convenient to have analytical formula, and maybe it's more difficult. So can you explain us why? I guess it's maybe more difficult to apply this approach with surface code or not?
So surface code, what I know is that it's mainly numerical approaches. Yeah, I don't know very well the surface code. I just know, so for instance, what I know is that in terms, for instance, of doing, I cannot give a good answer. I can give you, so there are comparisons about the physical resource required for surface code versus concatenated code. So for instance, in terms of difference, I know that surface code, if you have a high probability of error, which is the case here, because we take qubit about 1 millisecond, but it's typically a high error in terms of surface code will be less resource demanding. So it could, in terms of physical qubits, or logical qubits. So that's one thing I can say about this, but then I just know that it's numerical, the estimation of surface code.
So I think so. If I'm not mistaken, also in your manuscript, you in fact your estimate is so you consider a lot of noise of say costs, but in the end the dominant one, if I'm not wrong, is the cost of signal generation. And here in fact, in the end, your most of the results are really, I have the impression that rely really on this estimate that you will need 1 picojoule per bit for multiplexing the data from an optical fiber. So is this number really, I mean, can this number change over time? What can you say about this number? Because this will kind of dominate this like 5 milliwatt per operation.
So for me, I would say that the dominant one is not really related to multiplexing or demultiplexing. If we checked that they do not dominate, it's more related to the signal generation. So really generate the signal and this is typically 5 milliwatts per physical qubit. If you take state-of-the-art value, for instance, Google, there is a paper from Bardeen that did an experimental implementation of that. So now, and I would like also to say that it's true that the signal generation is important, but that's not only this, because in some case where we find the optimum, for instance, for signal generation being at 300 Kelvin, and there are many examples where we find that's the case, then there is the heat conduction that plays a significant role. So I think it's really the two that plays a significant portion in terms of the power consumption. So now in terms of reduction, of the so for the electronics, there are other approaches to generate signals. Some are based on superconducting circuit that generate signal, and in which you can reduce, if I remember correctly, so in theory, you can reduce by 1,000 the power consumption of that. There is also a diabatic circuit by 10,000. So that's other approach to reduce the bill of generating signals.
So can you? So we are in Grenoble, right? So it's interesting also to think about applying your approach to spin qubits, for instance. What can you say about that?
So for spin qubits, so I think, so first, a difference that I think will be important. So I read a little bit about spin qubit, but for instance, the need for attenuation is relatively different because the coupling, so in superconducting qubits, let's say the coupling between the qubit and the waveguide is high, and because of that, we attenuate. In spin qubit, I know that for single qubit gate, for instance, that's not the same issue. The coupling is very low, and because of that, you actually have to inject a lot of power, but you don't need, in principle, to attenuate. So that's first.
But this power, I guess, is dissipated somewhere anyway.
Indeed. Then you have, but let's say it's you don't need to dissipate, so you will attenuate less. For instance, that will be a first difference. There is also the fact that the qubit can work at higher temperature, which will definitely change aspect in the bill. One thing also that is important is that here, to use that code, we need long-range interactions. In spin qubits, from what I know, or maybe it exists, but I haven't found many schemes in which you can do long-range interaction with spin qubits. Usually you move them, so it's another strategy, but that will also be a difference. And then the typical power to generate the pulse also will be very different. So then it's analysis to do.
Okay, so
thank you. Now it's gonna be your turn. Azia, can you? Yeah, you're here.
Yes. Hi. Hi everyone. Thank you, Marco, as well for the very clear presentation. I also share Patrice's opinion about the topic. I feel like this is a very timely subject, and it's. I think your work is important in that respect, as it starts to put some. Gives a good perspective of what needs to be done with respect to the energy cost of the computation of the with this kind of systems. So I also have a few questions. So maybe just to pursue the questions that Patrice was asking at the end. So you mentioned that at the end you mentioned that this is computation based on superconducting qubits. I feel it's much more really the case of only transmon, right? I mean, because basically the energetics of a pulse basically is calculated by considering the fact that you need to change an energy level of a transform. So you could imagine any other type of qubit, which with a low frequency qubit, let's say fluxonium, perhaps, and then the computation is going to be completely different, right?
Yes. Yeah.
So have you considered that? Do you have any idea of what is actually good superconducting qubit in that respect? Only with respect to one pulse, you want to just do what is, if you want to do one operation, let's say a pi/2 rotation of your qubit, what qubit is the best with respect to the energetics of that? Or what kind of qubit you should use?
So yeah, I think in a way, so for instance, fluxonium, I know that they are more, so they are lower in frequency, so they are more sensitive to temperature. And because of that, you might need to cool them down more. And in an indirect manner, it could affect the power bill of that because you need to maintain them at lower temperature, so to evacuate the heat. So that's one difference I would see directly. Then for the typical power you need to drive a fluxonium, I don't know. I have to look at.
Okay, and okay, so yeah, I mean, in this first transitions, you don't necessarily have the. I mean, the two states are not necessarily coupled to each other, so I don't think the temperature necessarily is going to be an issue. But anyways, so you also, and the fact with respect to the temperature, you mentioned. The curves that you show, the color maps that you show with the temperature. So in your model for the temperature, so what kind of aspects do you take into account? So when you basically increase the temperature, so basically it seems like you mentioned that the optimal value would be to have maybe for some particular parameter regime, it would be to have a hot qubit. But so in that respect, what is the model that you would take into account for this hot qubit? Because we know that actually many things could go wrong when you increase the temperature.
Yeah, I agree. So in the model, we only took into account indeed the thermal noise in the driving signals. Now I know in superconducting qubits you also have the quasi-particles that can induce noise when you increase the temperature. So the behavior will be different if we enter in a more detailed model. But this is true for any part, all the elements in this model that we could improve the accuracy of the model. And but maybe I would also like to go back on the previous point because about the temperature. Because maybe in terms of the pulse you have to provide, it will be different, but you have other parts that enter in the bill, for instance, the heat conduction. And probably that directly, if you look at the power to do the pulse, maybe this will not be significantly different, but there are many other elements in the computer and they all participate in the bill. So maybe in an indirect manner, it can influence the cost.
So in your manuscript, there is a section where you speak about the long range crosstalks, and that you mentioned that it also can lead to some kind of noise. A scale dependent noise.
Yes.
Which is maybe breaking down the threshold theorem. So I had some questions about that. Basically, your analysis is based on these Aronoff-Kitaev-Preskill calculations.
Yes.
As far as I understand from Aronoff-Kitaev-Preskill's paper, they basically consider worst case scenario because in their case they want to show that there is a threshold, right? They basically replace their Hamiltonians by some worst case scenario. However, in your analysis, it seems like you use this worst case scenario to show that there is no threshold. So I was wondering if this is reasonable.
Okay. Yeah, I see what you mean. So
basically, they just replace the Hamiltonian by its norm. They basically forget the structure of the noise, right? some way.
Yeah, it's true. It's they take an upper bound on the scenario. So what I would say is that, so yeah, let me see just. So yeah, I would say that the philosophy of this calculation was mainly to do to take an example of when we can have a crosstalk and to let's say to show what kind of behavior it can give. Now it's what I will say is that it's also in some way the philosophy of fault tolerance. We never have access to the exact value of the thing. We usually have estimation which are based on upper bounds. So it can be possible indeed that it will not enter in this scenario, but in some way we take the best estimate we can have of the things, and that's.
So, I mean, in some way, you're also considering this worst case situation. You're saying that in the worst case scenario of this kind of long range interaction, we might have a problem with the threshold theorem. Is that right?
Sorry, can you repeat?
I'm saying in some way you're also considering a worst case scenario for this long range interaction somehow.
Yes. Yes.
I'm saying that not necessarily. I mean, as RNF-Kitaf and Prescott shows, basically you could still manage long range interactions in many cases. Okay. I think. Well, on the case of the, so I guess this question is much more relevant for the surface codes, but in general, have you considered, in this case, question of scale-dependent noise, to consider the structure of the noise as well? Basically, the fact that we increase the size of the system indeed can bring in some new noise sources, but usually they are very structured. There is a very particular reason for that. There is maybe crosstalks with the other qubits. There is the questions of the multiplexing in the signal generations and this kind of stuff. And maybe these kind of situations could be considered in a different manner than just brute force quantum error correction, right? I mean, you don't necessarily rely on the same error correction to take into account these. For example, you know, the Google group are nowadays discussing the possibility of this, I don't know, this correlated noise generation because of cosmic rays. And I don't think they consider taking them, taking them away using quantum error correction. They basically are trying to, by knowing that the structure of the, the reason the noise is there is this, the source of noise is here, you can maybe try to remove it in a different manner, right? So yes. In some sense, I feel like the question of scale-dependent noise becomes, a lot of scale-dependent noise is of this type, right? Of this structure type. Which could be maybe taken into account in a different manner. So yeah, I was just mentioning if you might have a opinion on this, or do you think it's,
Yeah, so indeed, scale-dependent noise, you can have different way to handle it. Then I think it's very system-dependent and noise model dependent. So in our way, it was indeed to consider, we keep the same code and we inject a scale-dependent noise and we see what happens. And we just try to see the connection. And then it was a first step for us to relate it to energetic estimation, which was the original goal. And then but then for me, that's a question to know if really by using those strategy, the noise will necessarily be bounded by using, maybe it will, maybe it won't. This I don't know, and I think it's a complicated question to answer.
Okay, thank you a lot. Again, I think this is a very nice first work on this topic, which is I think people should take care of. Really think about in a very careful manner. Thanks.
Okay, thank you.
Thanks, Nadia. Eleni, you ready?
Yes.
Yes. Yes, hello. Thank you very much. Hello, everyone. Thank you very much, Marco. That was an extremely interesting presentation. It was also an extremely interesting PhD to read. So for me and for, I think, most people, it was the first in-depth analysis of this question of energetic cost. And I find this is quite extraordinary, and congratulations. It is not in every PhD that somebody introduces a new field of research. So, so this is fantastic. So good. You did an excellent work. So I would like to ask a few questions as well on the topics that were mentioned today. I would like to follow up a little bit on the question. Actually, I had a very similar question to Maziar about Sycamore and about Google, the Google system. The thing that I remember when this Google the quantum supremacy results came out, there was a lot of discussion exactly about this scale-dependent noise, about how they kind of extrapolated in their claim of quantum advantage, how the noise would behave with a much bigger system, right? Mm-hmm. So this is obviously, as you said, an extremely difficult question, but in the end, the feeling, basically, to make it a more precise question, is like, how realistic do you feel that this noise model that you considered in your work actually do, because I feel that your results depend tremendously on this, right? And so if it so happens that the law of behavior of how this noise behaves is completely different, it would change entirely the orders of magnitude. Is this correct, my feeling? And what is your vision of this?
So just maybe to be sure to understand the question, so you're talking about the first work on scale-dependent noise with correlated, okay. So in this specific calculation, so I agree that what we wanted is just to have an example of, let's say, a physically motivated noise that grows with the size. So to see its effect on, because to say things precisely, so as I said, originally, the question was phrased for the question of energetics. But energetics, you can say I fix my amount of energy, but in terms of constraint, it's like a bit constraint that is a bit fictive. We can relate it then to estimate the energetic costs. But so that's why we wanted an example in which there is no such thing as I force to have a limited amount of resource, which is that one. And then we wanted to take a model that is relevant for that. And we took this model of long range correlated noise. Now, for sure, you could have a very different noise model, and maybe the noise. So, for instance, there is a discussion with this noise model about how fast it decreases with the distance between the qubits. And
that was another question I had since you mentioned it. Okay. I was also wondering what is if the role of nearest neighbors, right? That happens, that comes up a lot when we're talking about quantum computing, and it was kind of absent from your analysis.
Yes. So so what I will say to that is that for me this was just an example to illustrate the connection between scale-dependent noise and limited accuracy. It's not an in-depth analysis of all the effect of crosstalk you could have. This is so indeed experimentally, will you have this kind of noise, or will the noise be much more bounded? I can give you an example in which the noise will not necessarily be bounded. If you want to drive, so it will be a different model than this one. But when you generate signal, you can have wires that are close together, but a drive qubit that can be far away, for instance. And if you have crosstalk in those wires, it's not necessarily related to the one that are physically close. It's a matter of how you design the things, for instance. So clearly, this is not an analysis on all the kind of crosstalk you could have. It's just one example that's grow with the size of the computer.
And how about the actual analysis that you did? So beyond this, the analysis of the one that whose result we're seeing on the slide here, you know, the actual quantum computing energetic cost. Did you? Now I can't remember anymore. How does it depend on the noise model? You consider a realistic noise model, I understand, but you had to somehow take into account the law, right, for how it behaves. This is with a number, which is kind of speculation.
Yeah, you mean, sorry, just to understand your question, you mean what are the assumptions behind our noise model? Is that it? Okay, so yeah, it's we wanted to take a simple example. The only reason why the qubits are noisy is because of spontaneous emission and thermal excitation in the driving line. And it's true that you will have other source of noise, but that's, yeah, then it's a matter of improving the model, and then there is a lot of work if we want to improve the accuracy of all part of the model we use. But I agree.
Okay, I see. And did you check what the power consumption of the Sycamore Google was to see if it agrees with your results?
So the Sycamore, I think it consumed 10 kilowatts of power, if I remember correctly, and it's so it has 50 qubits roughly. I don't remember the exact number, but the thing is that to compare directly, so to check that the model we use is valid, actually I did not compare it directly to Sycamore for different reasons. The first reason is that so they don't use a kernel efficiency, they have their own fridge, and then it makes very complicated to know which efficiency we should take, because they have an efficiency that is very different and it might be dependent on temperature. So to check the model, the first thing I use is I compare my calculation to a paper made by cryogenics people that designed a 100 qubits quantum computer, and I compare all my value of heat conduction, attenuation in a non-optimal scenario, and it agreed with their calculation, and that's the main thing I did to check the validity.
Okay. Very good. Thanks. I have another question, which is also on a different, like you got questions about spin qubits and about surface codes. So my question now is, what about measurement-based quantum computing? So this is not everything that you have done is gate-based computing, the whole analysis. So, but MBQC is becoming quite popular, right? Especially for some experimental platforms. So of course, this will require another analysis. I'm not asking you to do it right on the spot, but can you give us some intuitions? Because in general, measurements were kind of a bit neglected overall, except for the very last calculation you did, where in the error correction, where there are some measurements of the ancilla qubits intermediary, so then you kind of took them into account. But in the MBQC, it would be a completely different, right? So can you give us some intuitions on this?
Yeah, so I don't know very well measurement-based quantum computing, so I cannot give a good answer.
Okay. I wanted another question as well. You didn't mention it a lot in your presentation, but in your thesis, you're discussing about the fact that when you did this optimization, this minimization, let's say, of your power under constraints, the configuration space was in general smooth, and you found a single minimum every time. And I found this a little bit surprising. For some reason, I would have thought with such a multi-parameter optimization and such a complex, like a thing with so many parameters, I would have thought that like a single minimum sounds too good to be true. Yes, how do you explain this?
It's true. Yeah, so I understand your question. It's true. I was also surprised by the fact there is a very well identified minimum in all the simulation I did. So my guess would probably be because actually there are not so much variable in the optimization. First, there are 4 variables, but some of them it's obvious that it won't be a good choice. For instance, if you increase the concatenation level, it is clear that it costs a lot more power, and so you should not do this on many points. For instance, there are other aspects which are for instance, if I think about the signal generation, its temperature, there is already a competition that is occurring purely from engineering parts. What I mean by that is that that's a competition. If you forget the noise, the colder you put your signal generation, the less heat conduction you have. But the more it costs you to evacuate the heat of that electronics, and that's the other way around. So there is already a competition here that already gives some tendency about this parameter. So I think that in practice, the parameter we have, some of them, it will, at first view, be unreasonable to put them on specific value, and then I guess it constrains a lot. Now, why there is exactly one minimum, this is complicated to be sure, but that's an intuition I will have on that.
I see. Okay. I understand. That makes sense. Okay. I think I have a kind of last a little bit approach question, a bit historic even question, and I would think I would like your opinion on this. So there is a little bit of contradiction in your approach in the sense, but I know it's a very difficult question, where for some things, at one point, you want to use your energetic cost so that you can guide the development of quantum computers now. But at the same time, you make some assumptions, extremely optimistic assumptions about, I think, so there is a little bit of a contradiction there, right? So you make some, so the idea would be that if this was true, well, then maybe, we wouldn't have to guide the quantum computers, like, for example, the gate fidelity behaving depending only on the qubit lifetime and this type of thing. So you make these things. So this is a bit of a remark more than a question. So it's a little bit. And then I was wondering, have you checked how the consumption of classical computers evolved, just to give us an idea of what may happen with quantum? From the times that we are now, right? 50 years ago, when a classical computer was taking a whole room, how has it evolved with respect to today's?
Yeah, so that's something I looked at some time ago. I know there is an equivalent of Moore's law for energetics in terms of watt per hour. But like this, I don't remember exactly.
Okay, we'll see. I guess we'll figure it out. Okay, thank you very much, Marco. That's all for me.
Thank you, Eleni. Okay. Maud?
Well, thank you very much, Marco, for the presentation of the PhD. I'm on the engineering side, and on the classical, I come from the classical computing side, so it's very interesting for me that you look at this energetic of the computation, because this is something that is very limiting currently in classical computation, and there are no reasonable solutions. And one of the first discussion that we had with Alexia a few years ago was like, if a quantum computer is going to spend more energy than classical, there's no interest in the quantum computer. So I'm very happy. This is really great. And this is also very daring. What you're doing is a hard topic, because this is typically a multidisciplinary topic, and you're not an expert in each of the field that you're looking at, and there's always an expert who will challenge you on his field of expertise. And so I really appreciate the approach and that they are talking about this problem. I also appreciate that you made some assumptions, and that you explain the choices, and you make decisions. What you showed us is that you are able to make decisions, because there are a lot of unknowns currently and we don't know where we're going to. And you made some choices and you're able to justify that. So thank you for doing that. Many questions. Many questions have been asked. The one that I was going to ask about silicon spin qubits was obviously asked, so I can't go with it anymore. Nonetheless, I've got one, which is in your schematics about all the questions that you took into account. You've got engineering. You've got a bubble for engineering, and I'm wondering what's hidden behind the engineering.
So here, I would say there is a bit of subjectivity, what we put in cryogenics, what we put in engineering, given the qubit physics, sometimes it can be. So in this model, what I mean by engineering was mainly the aspect of so the signal generation and the overall structure, like the fact that we will, for instance, I know that there are other approaches which want to do multiplexing with putting electronics where the qubits are, so we do not make that choice. So the fact that we do not make that choice in a way is in this engineering bubble. That's also, but that's how I would.
Okay, that's what we could call architecture.
Yes, architecture.
And in this engineering bubble, I was also wondering. So you said that you don't take into account the energy that is spent by the private electronics to do by the electronics to do the measurement.
Yes.
And there is one part that is questioning me. It's the compilation cost.
Okay.
Because at one point you've got the gates, and then you're going to translate them into a hardware language. And I was wondering whether this compilation has an energetic cost.
So indeed, I think the problematic of compilation will have a cost, but it will be likely to be a cost before the computation. In some extent, you can do this before. And what we are studying here is the cost during the calculation. So that's one way to present it.
Okay.
And yeah.
Okay. Okay. Sorry, I'll give you regarding your assumptions, I appreciate as a person trying to develop qubits, I'm very happy that you made optimistic assumptions about the qubits, because you take into account that we're going to make progress, which is what we're aiming at. So that's very interesting for me. I was wondering whether you could do the same regarding the quantum error correction codes, whether because at the moment we've got a surface code which is not optimized at all depending on the type of noise, or do you have some perspectives in terms of error correction codes?
So I know that indeed, for instance, so that's something that Mazia knows well, the cat qubits, for instance, for superconducting devices, they're interesting because they only need to correct against one kind of error, a bit flip, if I remember correctly, when we concatenate. And because of that, it can reduce drastically the overhead, because here we are correcting phase and bits, and yeah, it's induced a lot of things. There are also other techniques, like, for instance, flag qubits. That's another way to measure the syndrome, and you need less qubits than the one we are using in what we present here. So clearly, for me, there are a lot of improvements on the error correction part that are possible. Yeah, the philosophy of the work was really to be sure to not lack any information to build the complete model, and for that we wanted to have good basis to start. Yeah.
Okay, thank you. And so you're handing me over the last question. What is going to be your legacy? I mean, you have done pioneering work, and how are we going to use what you've done? What do you leave to the community so that we can reuse what you've done and we can adapt onto what you've done?
So first, I will say the general philosophy that you should relate the algorithm accuracy to the power consumption, because there you can optimize many things by doing this, and you can realize that things that you think are completely disconnected, actually they are connected because of that. So that's the main thing. Then I think it can, so as we just discussed, indeed, we could optimize further things, but it can give some intuition about what is costly, what is not costly. So to give an example, here for the superconducting qubits, we realize, and for me it's not obvious, that actually the attenuation, the heat dissipated in the attenuator, is not really a dominant problem in what we saw. It's that's one thing that is interesting, because I know that I've seen in various papers to put a lot of attenuation to be sure really that the qubit won't feel the noise, but actually it's not necessarily a problem to attenuate. So of course, if you attenuate of 200 dB at some point, it will become a problem, but those kind of general intuitions, because another one was that we realized that in many of the, if you take a Carnot efficiency, the power consumption does not depend that much on the temperature of the qubit, which means that it's not really a problem that they work at low temperature, because so in some plots, we realized that putting that at 10 millikelvin or putting that at the temperature of the optimum, which was, for instance, 100 millikelvin, the power consumption did not necessarily vary a lot. But this is point dependent, but that's an information that I think is interesting to know.
Well,
yeah.
Thank you very much.
Thank you, Maud. Okay, my turn. First, I would like to make comments. As everybody said, it's a really pioneering kind of difficult work, because you have many things to study, Yeah, to study. And in fact, when we look at your bibliography, oh, it's going to be really difficult. It's really dense, and I learned many things looking at your bibliography. But there is also some bad comment I would make. It's also because it's difficult to make this work. It's sometimes, and sometimes even a little bit often, I don't see really the link with the physics, because you have a really strong mathematical background, I would say. You really use it, and there is many things about this, and this is fantastic. And I won't really push what the others say, but sometimes, as an experimentalist and as a physicist, I was just missing the link with physics. And yeah, that's one of my points. Now, in fact, from your answer for the question, I just realized now that the energy cost was calculated during the operation. Because most of the time I was thinking there is a problem. And there is a problem about the energy cost, because let's now go to one of your typical calculation. When you say typical calculation is in terms of energy, we need 10 megawatt, but for 1 millisecond, so we need only 10 kilowatt. And as I said, I am an experimentalist. So first thing was how to compare this to the number of power that you need to cool down the system.
Yeah. So indeed, that does not take into account that process. But I will say that that's a cost that you have to pay once for all, the cooling down. Then it's a matter of maintaining this power is to maintain the temperature while the calculation is running. So indeed, you have a cost initially, but then if you use your let's say you need to cool down once. That's what I mean.
Yeah. Okay.
Yeah.
And what is approximately this power?
Yeah, I know it can be costly, but quantitative value about the power and I think it might be very dependent on how many qubits we have, because it will be related to the volume to cool.
Yeah. One of the, and this is also something I would like. So, for example, if we talk about pulse tube, it's in between, but not to go and being always at 10 millikelvin. It will depend on my second question. It's in between 10 kilowatt or 20 kilowatt. Okay. So this also, but as you said, it's not during the calculation. It's what you have always to pay in order to be at full temperature. And then from your introduction and also from your manuscript, I was like, oh, it's gonna be fantastic, because I will know a lot about experimental aspect on energy cost. And so you say it's page 161 when you talk about the architecture we consider. So first there was a dissipation in signal attenuation, so basically the attenuator. And as you said, this is not so important when we talk about power consumption.
So yeah, and the conclusion of the study was that okay.
So I mean, so stop me each time I say something. Heat conduction in all the cables connecting to the qubits. At the end, you say we can neglect that. Tell me if I'm wrong.
No. For me, it was they are different. So what I mean is that there were first the full model is well, we could have encoded the full model, but we made simplification of this full model, and we looked at what we can neglect and what we cannot. So there are, for instance, the cable connecting between the signal generation and the laboratory. We can neglect the heat conduction compared to the electronics that is on that stage. So then it makes sense to remove them from the model. But I think in the approach, we removed what we calculated thing to check that we can remove them from the model.
So exactly, it's where I want to go.
Okay.
It's so you neglected compared to what was the most energy work.
Compared to so it's always neglecting. So for instance, it's neglecting but taking into account the efficiency, the Carnot efficiency on the appropriate stage. So but yes, it's.
So if I take the lowest temperature stage, 10 millikelvin.
Yes.
And I add up all the things that you neglected. If so, you say neglected compared to, and it's basically to signal generation most of the time. So now, if I do not compare it, tell me really, because
so it depends, not necessarily always to. So let me remember actually, because Okay, maybe it's frequently two signal generation because that was the appropriate comparison to make with respect to what we wanted to neglect.
Yeah. So
Yes. Okay. Okay.
There is no
Yeah,
problem. But do you have an idea about the power to send to the 10 millikelvin stage?
Yeah.
If you want, I mean, the total one.
Mm-hmm.
Okay.
So,
how much is it approximately?
So it will mainly be due to the attenuation, because the heat conduction basically will play a role on the higher stages. If you below 10 Kelvin in the model, we use superconducting wire, and basically they conduct very low amount of heat, and that the attenuation that will play the bigger role. So then if you want to have a typical value, you have 10 to the power minus 11 watts for the typical value of power to send to a qubit. Let's say you attenuate it by 20 dB on the qubit chip. So you have to evacuate 10 to the minus 9 watts.
Okay, so 1 nanowatt.
Yes. So when the signal is on, and and taking into account the fact that we use very good model of superconducting wire.
Yeah, you specify this because I was like,
yes,
the really good experimental point. So you say for 1 qubit you need 1 nanowatt.
For one, if you drive a gate, you need 1 nanowatt with the model of cable we used. Yes.
Okay. And now you need one physical qubit.
One physical qubit if it's driven. Yes.
So now how many qubits and how many watts do you need, or milliwatts?
So if the signal are always on, let's say we have 10 billion qubits. That's one for the one example with the quantum Fourier transform. So then we have around the watts that temperature.
Okay. And then you know what is the cooling power of a fluid at 10 millikelvin.
So yeah, it's much higher than this. I totally agree. But this is not for me. That's not. I've put reference in which made by cryogenics that say it's just that the small cryogenics indeed today they are limited into that.
Yeah, for sure. But so just in my opinion, I was like, you're neglecting something which is absolutely really important in an experimentalist. But it was not. You were not dedicated to this work. Continuing this work is really fantastic. But I was really really going deep into this. So yeah, no, I think I'm gonna end up with this.
Okay.
Thank you.
Thank you.
And now I'm gonna give the award to the person, then Alex.
Bon, je vais parler en français.
Pionnier en français.
Donc, je n'ai rien préparé pour dire. J'ai oublié qu'on va dire quelque chose, mais je pense que c'est un travail très dur. On a galéré, on s'était battu entre nous, on s'était battu contre qu'est-ce qu'on trouvait dans la littérature, et je suis très content du résultat. J'espère que ça va être utile pour plein de monde. Une première étape, c'est comme une première étape pour aller plus loin. Voilà. Tu vas poser des questions?
Non. So, pioneering. Bon, moi aussi, je vais le faire en français. Effectivement, je ne vais pas poser de questions. Je suis tout à fait d'accord avec ce que vient de dire Rob. C'était quelque chose de très compliqué, ce travail. Parce que c'était aussi uncharted territory, et ça l'est toujours, en fait. On a un objet interdisciplinaire là, et du coup, l'avantage, c'est que chacun peut arriver avec sa propre vue sur les choses, ses propres outils conceptuels, et commencer à contribuer d'une manière constructive. Donc, je dirais pour cette première étape, c'était très bien d'avoir quelqu'un qui est ingénieur de formation comme toi, parce que tu n'as pas eu peur d'aller regarder la circuiterie, tu n'as pas eu peur d'aller regarder la cryogénie, et en même temps, parce que tu aimes bien les jolis circuits dessinés, tu as pas eu peur d'aller faire de la photographie. Donc ça, c'était vraiment très bien. Et je te souhaite bonne chance pour la suite. Je suis contente que cette thèse soit terminée et bien terminée, avec un résultat dont effectivement, moi aussi, je suis très satisfaite.
Okay.
Merci aussi pour l'encadrement dans la thèse. J'ai beaucoup aimé cette thèse et je suis aussi très content des résultats. Donc, merci.
Vous avez une salle ou pas?
Non, mais quand même, on reste pas.
Ok.
On sait que c'est plus simple avec les gens en ligne.
C'est une image c'est une équipe en français, c'est bon. Ouais, donc vous savez, le jury va se réunir et on reste ici dans cette salle. On n'a pas